Okay, we're continuing on here, chapter 17. We talked about balancing redox reactions last time. Then we got into really the heart of the chapter, which is galvanic cells. And again, a galvanic cell is really a redox reaction that's occurring, and you can pretty much kind of build the galvanic cell in the laboratory out of a couple of beakers. And typically, you'll have a solid electrode sitting in it, maybe like zinc. And in the solution, you will have a zinc ion solution with some zinc ions floating around, maybe some type of counter ion, maybe salt sulfate, connected through a voltage meter there and coming out to the other side. We got something like copper on that side there and some copper solution floating around in there. And usually connecting both sort of cells here is what is referred to as a salt bridge. And again, the salt bridge has an ionic compound in it, an ionic solution. I think maybe potassium chloride was the kind of one that was in that example we looked at. And the idea here is on one side of the cell, we have the anode where oxidation occurs. And what happens in that case is basically these solid guys jump into the pool, so they lose their electrons, they become ions, and they go for a swim. And the electrons obviously travel through the wire down to the other side of the cell, which is the cathode. And in that case, we have a little reduction happening. And as those electrons sort of come in, they will hook up with the metal ion that's in the solution, and that's going to cause it to jump out of the swimming pool there and become solid and get reduced in this case. As we talked about, the purpose really of the salt bridge is to make sure that we really have the cell potential or sort of the charge difference. You want to kind of think about it that way, sort of correct, and we don't get a buildup of the wrong charge that we don't want. There is sort of a greater sort of positive sort of area over here on the cathode side. Again, that's going to be really helpful in moving those negative electrons that way. Without it, as we talked about before, if you again were to just sort of pull your salt bridge out, what's going to happen is as we this side here goes through oxidation, you're going to get more and more ions that are going to drop into solution, become positively charged. As this reduction occurs over here, you're going to get a lot more of the positive ions jumping out of solution, and that's going to leave you a lot more negative ions on the right-hand side. Again, if you didn't have that salt bridge, thank you. And obviously, if we're trying to move negative electrons, that's going to be kind of like a no-go that way now with that greater kind of negative charge there. In fact, it's going to go, why am I leaving? I got positive over here, and it's going to be more attractive to that side. So that is why we see here, for example, the positive ion in the salt bridge usually will funnel down to the right there to the cathode side. That's going to help neutralize that buildup of negative charge, and our negative ion is going to drop into the other side again to help neutralize that overall positive charge. So we can kind of keep the balance of charge the way we want it to allow, again, the electrons to travel from one side to the next. We can calculate the cell voltage or cell potential by taking E of the cathode minus E of the anode. And this was the formula we talked about, I think, at the end there. And when we get these values, we do get it from an SRP table, which is a standard reduction potential table. And as we talked about, because they are standard reduction potentials, all the reactions that you see in that table that have E values, they are all reduction reactions. And obviously, in an oxidation reduction reaction, there's an oxidation part, which means technically speaking, one of those equations that you pull from that table is backwards. And if you were to reverse it, maybe make a standard oxidation potential, you would actually change the sign of the E. And the change the sign of the SRP value really on the anode one, right? And that's the one that gets changed. So um, that is, again, as we talked about, why this formula has a subtraction. that subtraction will basically change the sign for you. So if you don't want to worry about changing signs on your anode and you're just kind of interested in just calculating sort of the cell potential or cell voltage, you could just go to the SRP table, find the two things, decide which one's your anode and cathode, and pop it in there with a minus, and it will change the sign for you. If you want to change the sign, then as we talked about, you really should not subtract. Obviously, at that point, you should add those two values together if you change the sign. So as I mentioned before, you may just want to kind of choose one way and go with it, so you don't get confused, kind of going back and forth. Um, you don't want to worry about changing the sign. Like I said, just go with the subtraction. As long as you could correctly identify cathode and anode, it will change the sign for you by doing the subtraction. Again, if you want to change it. With that being said, though, if you were to reverse one of those reactions in the table, and obviously, let's just say we had, something like this, which obviously here is a reduction reaction. The E was negative 40 volts, big one. And if I were to reverse this and make this sort of the oxidation reaction here, we do change the sign and it would be positive 40 volts. Remember that really when you write the E value there associated with that reaction, it should be correct for how the reaction is written. So if you actually do reverse it, technically, if you were to give the E value for it, it should be obviously the opposite side. Any questions on any of that there? The other thing we talked about as well, you can use the SRP values to help you decide what should be your cathode and anode in a galvanic cell. The one that is more positive typically is your cathode. Remember as well, the side note on that is that's only if you are not given an overall reaction. So again, if you're not given an overall reaction, like maybe the example we did at the end, where it's just like, hey, you built a cell of these two things, the more positive one should be your cathode, the more negative one will be your anode. If you are given an equation or told how the reaction is happening, you should look at it and see who's being oxidized, who's being reduced, and then that would tell you your cathode and anode. Any questions on any of that there? All right. Then let's do this one here. A galvanic cell consists of magnesium in a 1 molar magnesium nitrate solution and silver electrode in a 1 molar silver nitrate solution. What is the standard EMF of the cell here? Again, that's basically your cell voltage is what it's looking for. This is some of the values you would find in an SRP table. Yes. Okay, let's take a look. So again, in this situation, we're basically just told we're making a galvanic cell out of these two things. Obviously, if it was not given to you, which it might not be in a lot of problems, you'd have to go obviously to that SRP table that's in your book. And we would find our two guys here. And in this case, we would look at the more positive one here. And again, that should be our cathode in this case. That would obviously leave this guy as our anode. So in this case, we're just looking for really the cell voltage. So if you wanted to, obviously you could just go into that equation. And again, cathode minus anode. And that means since I'm going to be subtracting, I'm not going to change anybody's sign, even though technically this guy here would be the one that would be reversed. So we're going to go with 0.8 volts minus a negative 2.37 volts. And that's going to give us 3.17 volts as our cell voltage here in this particular case. I didn't ask for it, but obviously if we were to write perhaps the balance equation here, since this guy would be reversed, we would end up with magnesium on the left there, this guy here, and this. This is now an oxidation reaction, which means our standard oxidation potential here would reverse if you were to sort of quote it for that equation, the way it's written. And this guy here would actually need to be multiplied by 2, as we have 2 electrons there. So it has to multiply that guy by 2. Gives us 2 silvers plus 2 electrons. Goes to 2 silvers. The other thing we talked about as well is if you need to multiply a half reaction by a common number, it will have no effect on the SRP value that you find in that table. So it will still be 0.8 volts in this case. That would give us our balance equation where our electrons should naturally cancel out. and our magnesium plus our 2 silver go to magnesium with a +2 and 2 solid silver. And obviously here at this point, if you did this, you could calculate E of this cell by, again, adding in this case, because we already changed the sign for us, and we would get our same 3.17 volts in this case. So basically what's happening here is our magnesium is sending over a couple of electrons there to our silver in that case. Questions on that? Okay. Now, when we talk about sort of cell potential, we're talking a little about cell potential, electrical work, and free energy to tie it back to our friend delta G. And the work that can be accomplished when electrons are pushed or transferred through a wire depends on the sort of thermodynamic driving force of it, which is our delta G. So one EMF potential difference or voltage is equal to, again, a joule divided by a coulomb. So 1 joule work produced when we are at different points has that potential of 1 volt. So ultimately, when we talk about work, the energy is equal to our work divided by our heat. Our work is equal to heat times our change in internal energy. Ultimately, what we could get is the maximum amount of work will equal our delta G value. So when a cell produces a cell potential that's positive, current can be used to do some type of work. So a positive E is usually a pretty good thing. You're going to get kind of a spontaneous type of process that's going to occur where you can use that energy to do some type of work. So that brings us to delta G and sort of the relationship between delta G and the cell potential. And we get that relationship here through a couple of equations. So let's take a look at these guys. Let's pop them up here real quick. There we go. So we have our delta G is equal to minus NF E of the cell. So here N is, as it says there, the number of electrons. Now, when we talk about the number of electrons, it is the total number of electrons that is lost on the sort of anode side and gained on the cathode side. It is not like you add up the electrons in each half reaction. So what I mean by that is, if we had something where this guy maybe lost a couple of electrons and then somebody else gained a couple of electrons, when we would look at this, there's 2 electrons there, 2 electrons here. N would only be 2 and not 4. So you don't want to add them total in each because those 2 electrons are the same electrons. They're the ones that are lost by the oxidation guy there that's getting oxidized, and they're the same ones that get gained by the other ones. So sometimes people want to add those together when they kind of look at them. But it is just the ones, basically, however you want to think about it, when they're being lost, the balanced number is what N should be. F is Faraday's constant, and here's the rounded version of that, 96,500, 96,486 if you want the real number there, but 96,500 is Faraday's constant. So when we look at this equation, obviously here, if we take a look at just the sign of everybody, we do know that if I have a positive E, F obviously is positive, N should be a positive number. So that negative in front is going to turn my delta G into a negative. And when my delta G is negative, that means we got a spontaneous process occurring, as we talked about in the previous chapter. So that is why positive voltage is good. It should thermodynamically favor a spontaneous process to occur. And that means that you will be producing some electrons that could be used to do some type of work. Obviously, the opposite is true. If we take our delta G and we end up with a cell voltage that is negative, once again, that's going to be positive, that's going to be positive, and that's going to be negative. So those 2 negatives will now turn my delta G into a positive value in this case. And obviously, as we know, a delta G that is positive is a non-spontaneous process. So If you have a negative cell voltage, that will basically favor a non-spontaneous process to occur, which doesn't favor much happening. And obviously, you would not get the flow of electrons and you could not do some type of work, right? The good news is if you ever hook up like a galvanic cell and you get a negative voltage, all you need to do is just switch them around, right? Because it switches the signs of everybody, then you will have a positive voltage. Kind of like if you throw a battery in backwards, right? It doesn't work so well, but if you flop it the other way, now you're good, right? You just kind of made a non-spontaneous process or spontaneous there by getting everybody in the right direction. So those things, again, like all other things, should agree with each other. So you really can determine whether or not a reaction will sort of be spontaneous by looking at the E value there for the cell. And again, if you get that positive one, you should ideally get a negative delta G, and you should expect it to be spontaneous. You could also calculate, obviously, the Gibbs free energy associated with that as well. Now, of course, this class wouldn't be a class without our friend K and the equilibrium constant. So there's also a relationship between the equilibrium constant and E of the cell. And E of the cell is equal to RT NF natural log of K. And these are some of our normal ones here. This is our R value, our gas constant that has energy. So it's the 8.314 version of it. T obviously is in Kelvin, N is our moles, and obviously F is our Faraday's constant, which is the same Faraday's constant that's above there, and times the natural log of K. So, these things also kind of relate to each other. Obviously, if you have a large value of K, that's the only way to get that is a lot of products. And the only way to get a lot of products is you need a spontaneous reaction, which would probably imply that you got some positive voltage happening in that situation. Opposite is true as well. If you have a small value of K, you probably have more reactants than products, which probably means you're not heading to the product side, probably more of a non-spontaneous process happening, and probably some negative cell voltage. So these two versions of the equation are at 25 degrees Celsius, basically. And at that point, a lot of these become constants. So you could calculate E of the cell as 0.0257 volts over N natural log of K. Or if you like the traditional base 10 log there, you can do 0.0592 volts over N log of K. If you don't want to worry about these two equations, just put all the numbers into this top one, and then you'll obviously get the same answer, right? So you can just plug and chug into the top one and not have to worry about that. But sometimes people will sort of show these formulas. I think in your lab manual they use this one, I think, or one of these two, I think, maybe when we get that experiment next. So sometimes you'll see those, but they're really just based off of this guy, which, as we will see shortly, is based off of another equation. So this is our sort of a electrochemistry thermodynamic trifecta here. So if you have E of the cell, that would allow you to calculate delta G RK by obviously using the appropriate equations. Obviously, we could calculate if we have G, we could get K, or K, we could get G from the one we saw in the previous chapter. And again, so these are our three sort of formulas that relate each other to one another here. Any questions on that there? So as we were just talking about here, looking at these equations, again, same idea. Positive E should give us our negative delta G, which should be spontaneous. That should favor products. And if that favors products, that should also favor a larger value of K. If we have a negative cell voltage, that's going to favor a non-spontaneous process to occur. That means we should mainly have reactants. And if we mainly have reactants, we should expect obviously a small value of K as well. Obviously, you have no cell voltage, then, we don't got much going on there. We're sort of equally favoring reactants and products in this case. All right, so why don't you give this a go? Let's calculate the delta G for this reaction. Here's some SRP values down here. So obviously we are calculating the delta G. So might as well use that equation. Seems good. All right. So we do need to calculate the E of the cell. So we got our SRP values. In this case, we do have an equation. So that is +2 to 0. So that is being reduced, and this is going from 0 to +2. That is being oxidized. So by the way, you did have a reaction here. You should have looked at it, but if you didn't, you got lucky in this case because this is still going to be your cathode in this case. And this is going to be your anode. So just a reminder that if you do have the equation, you should look at it because it may not follow cathode anode rules there. So again here, I'm going to just subtract to get my cell voltage. So I am not going to change the sign again. If you want to change the sign, you should add as we talked about. So we're going to go cathode, which is 0.34 volts, minus our negative 0.44 volts. That's going to give us our cell voltage at this point, 0.34 minus and minus 0.44. Looks like a 0.78 volts. Obviously here, this one would be reversed, but at this point they are still balanced in terms of electrons, so they both have the same, and then that would mean in this case that N is equal to 2, once again, not 4, so N is equal to 2 here. F is a constant, so that's our 96,500 joules per volt per mole, and I think that's everything we need here, so delta G naught is going to be minus 2 moles are 96,500 joules per volt per mole, and are 0.78 volts. Volts are cancel, moles will cancel. Going to leave us in units of joules at this point, and that's going to get us here 0.78 negative 150,540 joules, or about minus 151 kilojoules. Yeah, as delta G is usually given in kilojoules. First off, any questions on the calculation? Again, certain things agree with each other, right? We have a positive delta, positive E, which leads us to a negative delta G, which leads us to, yes, this is going to be a spontaneous process, right? And really, we could have figured that out just really from the cell voltage, but in this case, we did want to calculate the delta G value in this case. Any questions on that there? All right, so why don't you do this one? Will 1 molar nitric acid dissolve gold metal to form some gold 3 ions? There's some of your SRP stuff on the bottom there. Okay, so let's take a look at it. So in this question, we're looking at whether or not nitric acid will dissolve gold to form some gold 3. So we want to figure out our cathode, anode. A couple of ways we could really figure out, will it or not. We could definitely calculate our cell potential. If we wanted to as well. We could also go the extra step to verify by calculating our delta G. So in this case, we're going to calculate our E of the cell. So we want our cathode. And in this case, cathode is this guy right here. This is our cathode. And this would be our anode in this case. Yeah. Any baby saying, but wait, isn't this one more positive? The answer is yeah, it is more positive. But in this question, it is asking, will nitric acid dissolve gold metal to form gold 3, which means that gold 3 is on the wrong side there. It actually needs to be on that side. That means this one is technically the one that needs to be flipped around. And if it does, now it is a oxidation, and now it's an anode reaction. So again, it's important to make sure you read the question, and definitely if they give you something in words like this, or they give you the overall reaction, that you actually take a look at it. So with that being said, now that we have sort of our correct cathode and anode, we could then calculate our E of our cell in this case, which would be our cathode, which would be 0.96 minus, and again, I'm not going to change the sign, so 1.5 volts. And that's not going to look so great, I think, for this outcome, but we'll see here, negative 1.5. Got a negative 0.54 volts with right there with a negative E. That's going to be a non-spontaneous process, and that's not going to work. And we know that because if we throw it back into our delta G, our N in this case would be 3. Our 96,500 joules per volt per mole, which is our F, and obviously our negative 0.54 volts. The negative there and the negative there is definitely going to turn our delta G into a positive, which obviously means it's non-spontaneous. So this will not work, right? And you cannot do that. That is how they used to test gold when you take it into the pawn shop. They throw some nitric acid on it. And if it's still there, hey, you got some gold. If it's not, oh, well, maybe you should find something else to pawn at that point, right? So that's a common test to test that as well. Because gold is obviously a noble metal, right? Very unreactive. Yeah, so you need a lot of strong stuff there to get it to react. Any questions on this one here? All right, then let's take a look at the next one here, which is um, what is the equilibrium constant for the following reaction? And there's some SRP values, I think, for you. Okay, let's take a look. So obviously we're looking for the equilibrium constant, so we want to roll with our equilibrium constant one. So a little RT/F natural log of K there. And so we need a couple of things here. Obviously, we need E of our cell. We're looking for K. R is a constant. Our temperature needs to be converted to Kelvin. So that's going to give us a 298. As was the question a second ago, N in this case is going to be 2 since they kind of gave you the half reactions here. And we do have our SRP values here from our table. And this is also a really good reminder of what we were just talking about in the previous problem. And that is um, we do want to look at the equation here. So in this particular case, iron is +2. The silver here is 0 in terms of its oxidation state. The iron on this side is 0, and the silver is +1. So in terms of the iron, it's going from +2 to 0. So it is being reduced. And again, if you kind of even need to do the number line thing like we did before, +2 to 0, obviously becoming more negative in this case. And by default here, we can see the silver is going from 0 to +1, so becoming more oxidized in this case. And that is different than, again, by going to by the more positive value here. So again, you don't want to go by the more positive value. You do have to look at the equation. And that would be here that this guy is our cathode because he is being reduced in the equation. And this is our anode, which once again is opposite of the more positive that we have here from the SRP table. That means correctly here, our E of our cell should be our cathode, which is our iron, which is negative 0.44 volts, minus our anode, which again, I'm subtracting, so it's going to change the sign for me. So I won't change it, which in this case is actually the silver. And here we will get, looks like, negative 1.24 volts in this case, yeah, as our E of our cell. First off, any questions on that? So again, make sure that you do look at the equations because if something else is going on in there, that's not going to work so well. All right, I think at this point we got everything we need. F obviously is our constant, our Faraday's constant, 96,500 joules per volt per mole. So if we pop in there, negative 1.24 volts is equal to, again, 8.314 joules per Kelvin per mole. Our temperature of 298 Kelvin divided by our N, which is 2 moles in this case, and our 96,500 joules per volt per mole. And that's going to give us the natural log of K. Just going to clean up, I think, before the natural log there. So we'll go 8.314 times 298 divided by 2 divided by 96,500. If I punch the numbers, that would be even better. That's going to give me negative 1.24 volts is equal to 0.012837 natural log of K. I'm obviously going to take this guy back over that way. And that will give me negative 1.24 divided by my number there. And that's going to get me the natural log of K is equal to negative 96.595, we'll call it in that case. At this point, Kelvins cancel, moles cancel, all that good stuff, joules cancel, all those things are going to cancel out basically. We're going to E both sides to fix that. So we're going to go E of both sides. That gets rid of the natural log. So our K will equal something like 1.12 times 10 to the minus 42 in this case. Any questions on that? Now, I will tell you when you're using some of these equations, especially when you get to this point here, depending on how you round, you may get a slightly different number if if you round a little bit more than I did or not. I just typically use the whole number, but if you do a little bit of rounding, you'll get slightly different. This number should still be pretty much the same, but that front number might be slightly different. First off, any questions on that there? So what we know about this reaction is things do agree. So this is a non-spontaneous reaction because we have some negative cell voltage, which should give us a positive delta G, which means the reaction is non-spontaneous. And because of that, it should be sitting on the reactant side as favored. And because the reactant side is favored, when you do products over reactants, you have a lot more reactants than products, and you should end up with a small value of K. So again, all those things should agree with each other. Questions on that? All right, so let's talk a little bit about the effect of actually cell concentration on the cell potential. And we do have sometimes non-standard conditions. And obviously we saw some of our delta G ones from the previous chapter that involve sort of non-standard conditions. Remember that sort of non-standard delta G there, standard delta G, and then we have our Q. And if we take some of our delta G and E guys and relate them to each other, putting all those guys kind of together yields us the Nernst equation. And the Nernst equation is sort of the galvanic cell version or electrochemistry version of like non-standard conditions and standard conditions, if you will. So this is E of the cell under sort of non-standard conditions is the way you could kind of think of it. Remember that this guy here is under standard conditions. So that's going to be in your SRP table there, cathode minus anode. The rest of it here is obviously what we just used in the previous problem. And our Q is again our reaction quotient, which is our products over our reactants. So remember, sort of standard conditions means that if you're dealing with any type of concentration, everybody is 1 molar. If you're dealing with any type of pressure, everybody is 1 atmosphere. So again, if you come across a situation where maybe you don't have 1 atmosphere or 1 molar for all the reactants and products, that should put you here to our Nernst equation. Just like that previous equation we saw at 25 degrees, you can reduce it down if you want to. Or once again, you could just ignore those bottom 2 equations and just plug everything into the Nernst equation and just get the answer. Obviously, it'll come out the same. By the way, that is how we got to the equilibrium equation we just used, because much like what we did here, at equilibrium, E will equal 0 and Q will equal K. And if you put that in there, 0 equals E naught minus RT NF natural log of K. Taking this whole thing and moving it to the other side gives you that equation we just used in the previous problem, which is here. Also, why, by the way, why there is no negative there as well. So again, there is a negative here, but not in that one. So sometimes people like to put the negative in that bottom one or the one we just used. But by rearranging it there, we don't get the negative that should be in there. questions on that. So this would be the equation that you would use to see, if maybe you play with the concentrations of your anode compartment or cathode compartment, or maybe some pressures if some of your electrodes were gas, and see if it can maybe make a non-spontaneous cell into a spontaneous cell by playing around with it. All right, so why don't we try that there? We got our SRP values. We got some concentrations. So we want to know, will this reaction occur spontaneously? Take a moment or two there and see what you come up with. Look at this. So in this case, we want to know, will this occur spontaneously? Um, we have some concentrations given to us. The first thing you should notice is that is not 1 molar concentrations. So we're not at standard conditions here. So a little Nernst equation would be a good move. A little minus RT NF, natural log of Q. So we got a few things to calculate here. We want to calculate, obviously, our E's of our cell here under standard conditions, which would be E of our cathode minus E of our anode. Again, here we have our SRP values given to us, but we also have an equation. So we want to look at the equation, see what's going on. That's a +2. That is a 0 for the oxidation state. That's a 0 and a +2. So our iron is going from +2 to 0, which means the iron here is being reduced. The cadmium is going from 0 to +2, which means it is being oxidized. So that means that the cadmium is my anode and the iron here is my cathode. So once again, you want to make sure that you do follow what's going on in the equation if it's given to you. That's going to then put us into here, our cathode, which is negative 0.44 volts, minus a minus 0.4 volts. Once again, here I am not changing the sign because I'm subtracting. And if you're adding, you should have changed the sign, hopefully. And that's going to give us here negative 0.04 volts, I believe. Yep. And under standard conditions, right, this reaction is non-spontaneous, right? Because with a negative voltage, that should give us, again, our positive delta G, and not so good in terms of spontaneity. But we're not under standard conditions, we're under non-standard conditions, so we do need to calculate this E to see if maybe those concentration differences will help us. Obviously here our temperature is going to be, again, 298. Our N in this case is going to be 2. I know that because I'm dealing with iron 2 and cadmium 2, which means they both lost 2 electrons. So N would be 2 in this case. Let's see here. F obviously is our constant. And in this case, we do need Q, which in this case would be our cadmium divided by our iron 2. These guys obviously are solid, so would not be included. Also, why you don't obviously have any type of concentration, because they are not solutions. We'll put in our values there for our cadmium, which would be 0.01 and 0.6 here, it looks like. And that's going to get us 0.01 divided by 0.6, 0.1, sorry, 0.01667. All right, so that is everything, I think. Time to put it into the big equation there. So E is going to equal negative 0.04 volts minus 8.314 for our R, 298 for our temperature, our N going to be 2 moles, and our F going to be our constant, and natural log of our 0.01667. So I'm just going to kind of clean up this part of it, I think. So I'm going to take the natural log of the 0.01667. Then I'm going to times it by 8.314, times it by 298, which is up on top. Going to divide it by 2 and divide it by 96,500. That's going to give me now that E is equal to negative 0.04 volts minus a minus 0.05256 here. And now I'm going to take the front part there and see what we end up with. And we're going to end up with a whopping voltage here of 0.013 volts. That means that this reaction now is spontaneous. Yeah, not a lot of voltage, but you got something in the positive direction you can hang your hat on. So by again playing with those concentrations, it could have a direct effect on whether or not, you can maybe make this galvanic cell work for you. Again, we didn't generate a ton of voltage, but we did get into a positive voltage, which technically would mean we would get somewhere of a negative-ish delta G, and should be a little bit more spontaneous. Any questions on that one there? All right, we're laid up there for now.